Hello everyone, thanks for joining us in IEEE WCNC 2022. My name is Asil Koch and I am a PhD candidate at McGill University. Today I'll present our paper named as Energy Efficient Throughput Maximization in mmWave Multi-User Massive-MIMO-OFDM Systems using Genetic Algorithm-Based Resource Allocation. Here is the brief outline of the presentation. After the introduction part, we'll present the system model, then the hybrid precoding architecture, and the proposed genetic algorithm-based resource allocation technique are expressed. And after the illustrative results, the presentation ends with the conclusions. In the wireless communications, the rapidly growing traffic rates and the user demands can be fulfilled by advanced transmission techniques, and MIMO is one of the key enabling technology. It has been an already integral part of the existing wireless standards such as 4G, 5G, and Wi-Fi. And around a decade ago, there was a paradigm shift in MIMO technology called as Massive MIMO, where we place excessively large antenna arrays at the base station to achieve higher spectral efficiency, energy efficiency, and enhanced coverage. The precoding is an essential signal processing technique to ensure a reliable transmission. And different from the single-stage, fully digital architecture considered in the conventional MIMO systems, two-stage hybrid precoding is a promising solution for the massive MIMO systems because it significantly reduces the number of RF chains, considering we have large antenna arrays, and it can reduce the hardware cost, complexity, power consumption, and the channel estimation overhead size. Here is the system model. We consider a OFDM-based downlink transmission with C subcarriers, where the base station is equipped with a uniform rectangular array having M antennas to serve K single antenna users clustered in G groups. Here we have a single RF beamformer block because the RF beamformer is designed based on the angular information, and in each subcarrier, the angular information is similar. And then the RF and baseband stage are connected with NRF RF chains, and then we have C sub-blocks for each baseband precoder and the power allocation matrix P. And then the transmitted downlink signal vector S is defined as in here for each subcarrier. And then the receipt signal at the kth user for the ith subcarrier is the combination of the desired signal plus inter-user interference and noise. Then we can define the sum rate expression accordingly, and then the throughput maximization problem is given in here as a function of the RF beamformer, baseband precoder, and the power allocation matrix. However, this is a non-convex problem. That's why we sequentially solve the F, B, and P matrices. Also, we consider 3D geometry-based millimeter wave channel model. Due to the limited scattering in the millimeter wave channels, the channel model is defined in equation 4 as a function of the fast time varying path gain information and then the slow time varying angular information. And here the phi matrix is the phase response matrix, and it is a function of the AOD parameters. Then the channel is composed of two parts, having the fast time varying CSI part as the channel H, and then the slow time varying part as the phi matrix. Okay, let's start with the design of the hybrid precoding part. We first developed the RF beamformer. Considering there are G user groups, we use G sub-blocks to develop the RF beamformer. Then the effective channel seen from the baseband stage is going to be the multiplication of the full-size channel matrix with the RF beamformer. Here, the block diagonal matrices represents the effective channel for a given user group, whereas the off diagonals represents the effective interference channel between the user groups. And to maximize the beamforming gain in the desired direction while suppressing the intergroup interference, we need to satisfy two design criteria given in here. Here we utilize the steering vector defined in equation 8 according to the URA structure. Also, we define the orthogonal quantized angle pairs to cover the complete 3D azimuth and elevation angle support. Then The RF beamformer block for the Gth user group is defined by using the steering vector and the quantized angle pairs covering the corresponding AOD support. Then the effective channel seen from the baseband stage is utilized at the baseband precoder design. Then the channel estimation overhead size, considering we have M antennas and NRF RF chains, is reduced from K times M to K times NRF for each subcarrier. Then the baseband precoder is developed by using the well-known regularized zero forcing technique as in equation 12. Afterwards, now we develop the genetic algorithm-based resource allocation. Here, for a given RF beamformer and the baseband precoder block, the new throughput maximization problem is defined in equation 13. Here we try to maximize the capacity by choosing the optimal allocated powers for each subcarrier. However, this problem, even though we solve the RF beamformer and the baseband precoder, this problem is still non-convex. And here our motivation is to allocate the power and the subcarrier resources among the users to maximize the capacity. In order to solve this non-convex problem, we apply the genetic algorithm. It is inspired from the Darwinian theory of the evolution to address the shortcoming of the traditional optimization techniques. And the genetic algorithm can be utilized to solve non-convex optimization problems. And the algorithm actually evolves through generations, and each generations of each existing chromosomes. And then we here consider Q generations to evolve NP chromosomes. And this algorithm actually has three main parts: the selection, crossover, and the mutation. And in order to represent our resource allocation problem, each chromosome actually represents the power allocation block given in here, and then we try to we define NP chromosomes, and we apply the selection, crossover, and mutation for every generation to maximize the overall system capacity. This slide summarizes the proposed genetic algorithm-based resource allocation technique. The first phase is the initialization. We randomly generate the chromosomes, in other words, the power values. Then in the second phase, we apply the selection and the crossover process. First, the top row mating percent of the population is chosen to form the mating pool, and the rest of the population is discarded. And then we apply tournament selection approach to choose the parents, and then according to the given set of parents, we apply the linear and the uniform crossover. As a mixture of two crossover methods, we apply the crossover as well. And then after finishing the selection and the crossover, we apply the mutation. And this process, actually the selection, crossover, and mutation process is applied for Q generations. And after Q generations, the best member of the best chromosome in the last generation is chosen as the optimal solution. And then we form the power allocation block for the ith subcarrier. And here epsilon represents the normalization scalar to satisfy the transmit power constraint. Now we move to the illustrative results. Here we present the sum rate as well as the energy efficiency performance of the proposed GA-RA algorithm for the multi-user massive MIMO-OFDM systems. The simulation parameters for the 3D microcell scenario is given in this table. Just to highlight some important parameters, we consider there are 256 antennas at the base station, and the cell radius is 100 meters, and we have 3 user groups, and the users are equally clustered in each group. And for the GA-RA algorithm, we have we consider the population size is 100, and then we have 10 generations. In the first illustrative results, we plot both the sum rate and the energy efficiency results versus the number of subcarriers. Here, we compare the hybrid precoding schemes with the fully digital precoding. In the fully digital precoding, the number of RF chains is equal to the number of antennas. That's why we need 256 RF chains, whereas the hybrid architecture requires only 36 RF chains. That means 87% reduction in the hardware complexity, as well as the channel estimation overhead size. Also, for the hybrid scheme, we consider 3 scenarios. And the first one is the proposed GA-RA algorithm, of course. The second scenario is the PSO-based resource allocation technique proposed in reference 9, although it was considered for the single carrier transmission. Now it nevertheless served the benchmark, and we compare this one as well. And the last one is the equal resource allocation among all subcarriers. And if we compare the hybrid precoding with the fully digital, we observe that there is a slight degradation in terms of the sum rate performance when we compare the hybrid precoding and the fully digital precoding. But on the right, we have also the energy efficiency results, and in the energy efficiency, the sum rate is we take the ratio of the sum rate with respect to the total power consumption, including the transmit power, the power consumption by RF chains, and the power consumption by the phase shifters at the RF beamformer. And now when we look at the energy efficiency results, due to the power-hungry RF chains and the large number of RF chains in the fully digital architecture, the hybrid precoding enhanced the energy efficiency greatly compared to the fully digital architecture. Okay, and now when we look at the proposed GA-RA algorithm, it greatly enhanced the sum rate capacity as well as the energy efficiency in comparison to the equal resource allocation, as well as the benchmark scheme as the PSO-based resource allocation. In the next illustrative results, we plot the sum rate per subcarrier versus the transmit power, and we consider 2 scenarios as 8 subcarrier and 64 subcarrier. And here, the GA-RA algorithm is compared again with the equal resource allocation, and here for GA-RA we consider either 1, 5, or 10 generations. And we observe that when we have low number of users, it directly converge in the very first generation. But on the other hand, as long as the optimization space enlarges for the large number of users, it requires more generations to converge. The last illustrative results plots the sum rate per subcarrier versus the number of subcarriers for different transmit power scenarios. And here, what we observe, the gap between the genetic algorithm-based resource allocation and the equal resource allocation remains almost constant as long as the number of subcarriers increases. And when we look at the sum rate gain ratio, it increases for the larger number of subcarriers. In conclusion, a new genetic algorithm-based resource allocation technique is proposed for the multi-user MU-MIMO-OFDM systems. And here the hybrid architecture has 3 stages as the RF beamformer, baseband, precoder, and the multi-user resource allocation block. And we show that the GA-RA algorithm greatly enhanced the energy efficiency as well as the sum rate with respect to its benchmarks as the PSO-based resource allocation and the equal resource allocation. Here are the references. And this is end of my presentation. Thanks for listening.